Welcome to the School of Biomedical Engineering Undergraduate Teaching Lab, where we run labs from the gamut of cellular and molecular engineering to biomechanics to bioelectrical and beyond. This gives you just a glimpse of our lab space, our benches. Currently, we're equipped for online teaching, one of our resident skeletons, biosafety cabinet for cell work, some sample preparation area, a couple 3D printers we use in one of our labs.
So this device is an electromyography device, or EMG, and it measures the electrical output of muscles. And so if we have one of these systems and hook it up, for instance, to a muscle, so these are where I have some electrodes placed on my bicep muscle, this system can communicate with this computer. And so when I contract my bicep muscle, what we see is a little burst in electrical activity that we're measuring with this system. And so that's a voltage that's being measured. And so when I contract my muscle, we see a little burst in that electrical activity. When I rest my arm, it calms down. When I contract again, we see another burst, again relaxed. And so that's useful in biomechanics to figure out the contribution of muscles to various things that we're doing biomechanically. The muscles play a big role in determining the joint forces that we have. They play a big role in determining risk of injury, pathology, its influence in arthritis. For sport biomechanics, it plays a big role. So this is an interesting side of biomechanics to look at the role of musculature. This is a system we use. It's a Benchtop materials testing machine, and so it has what we call a load cell, so that's able to measure force at the top of it, and it also has some equipment in it that measures displacement or distance. And so using that information, we can study something called stress and strain, and that's something that's important to understanding the behavior of various materials. So we would do something like this, a test like this, to understand the mechanics of how bone would fracture. We could study the effect of load on an implant performance. So if we're looking at how, for instance, a hip implant would work inside the body, we would use a bigger version of this system to test an implant like that out. We can stretch various materials with this. So this is an example of some tissue that we have in the lab, some synthetic tissue. This is a rotator cuff tendon. So it's a tendon in the shoulder joint. We have some skin tissue as well, and so we could cut out a little piece of this and put it in the machine and study the mechanics of how that tissue would stretch, at what loads it would rupture, at what forces we would expect a tendon to rupture, so we can really understand how the biological materials would stretch under physiological loads. So this is a motion tracking system. It's an OptiTrack system called 3D Investigator. And you can see it has 3 camera lenses on it, so they're all mounted to the same unit, and that gives the ability of the system to triangulate the position of a marker in space. So essentially we can track the 3D position of where a marker is. And so these are what an example of what a marker would look like. There's one, and there's a set of 3 right there, and these are infrared light, or they emit infrared light. And that's something that the system can detect with these lights that are flashing. And so they can pick up where they are in space, and that allows us to track motions that are related to biomechanics. We can do some biomechanical analyses with those. This is the same system that's used in designing video games as well, and some of the computer animated movies that you've seen, such as Lord of the Rings. Some of the characters were recorded using a technology such as this. if you're playing video games and you have a golf game, for example, they would likely have put a bunch of markers on Tiger Woods, and they would measure the motion that he does while doing a golf swing. And so that's a technology that we also use in biomechanics. So in this lab, we have a unit like this, and we have a bunch of markers, and we can suit people up and get them to do various things in the lab and record their 3D motions while they're doing that. This is a depth sensor. It uses structured light to figure out the depth of an object. So you can see there's 3 little windows here, and that uses a combination of some cameras and projectors to send out light toward an object, a pattern light, a structured light, and then the way that pattern returns to the system, or the way that it detects that pattern returning, helps it figure out some depth information. And so if we look at this image, we can see that this camera's applying, looking at the depth of where I am. And if I back up, the system now is smart enough to detect where my joints and body segments are. And so you can see as I'm moving, it's following more or less my body parts and my joints. This system is using some smart algorithms such as machine learning to figure out, it's seeing these blobs at a depth, and what it's doing is it's using prior knowledge of the shape of, for instance, an arm, or where an elbow joint may be, and then it's using that information to determine where my elbow is likely to be. And so it can follow what I'm doing. This system is these types of systems are originally developed for the gaming industry, so for video games. And so they've been pretty fun to use in that field. And this is just recently being applied to the biomechanics field. And so because it was originally developed for games, the precision is not as critical as it would be in biomechanics. So the advantage of a system like this is I don't need a marker system, which has a lot of advantages to it. The disadvantage to this system so far is that the precision accuracy is not quite there yet. And so this is certainly where the future of biomechanics is going, but there's still a lot of work to be done in terms of improving the algorithms and the accuracy of its ability to track human motion.